and what you're doing in the talk. So just very briefly, Terry is I suppose you're a professor of architecture, aren't you, Terry? Or what are you officially?
Yeah, that's a good question. We give ourselves our own titles at MIT.
So what title have you given yourself?
Professor of Design and Computation.
Okay, but you're in the architecture faculty.
Yes, I am.
Yes, I've met Terry over 20 years ago when I got very interested in shape grammars, which I think, as Terry will tell us, are very interesting about understanding the structure of how designs come together. And ever since I followed Terry's work, which was thinking both about theoretical issues and practical issues, so I thought that would be of interest to a lot of our community, even though I think Terry is slightly outside the range of people who normally attend our engineering design conferences. So I suggest we hand over to you. Maybe we could all turn our cameras off for Terry's talks just to sort of save some bandwidth. So I'll turn mine off, and or Terry, do you want me to keep mine on so you can talk to the little Claudia in the corner?
The what?
The little Claudia in the corner.
I can talk to the little Claudia. Yeah. Thank you, Claudia.
Okay.
Can you hear me okay? Everyone hear?
Yes, we can hear you.
I very briefly, when I stopped sharing my screen, I very briefly saw some names, and I think I saw Martin there. So if Martin's there, hello, Martin. But I only see Claudia right now, which is fine. I don't see myself. Thank you, Claudia. And thank you, Ross, for inviting me to talk to you today. It's really nice to connect with people that I can't see in these COVID times. So hello to all of you wherever you are. You can see me, I'm sure, and welcome to the third floor extra bedroom in my house in Brookline, Massachusetts, where I've been since March, at least been since doing my work since March, and it looks like it's going to stay that way for another few months at least. So anyway, thank you, Claudia, for giving me the opportunity to look back at my work. And as you asked me to do, I reflected not just on what I've done, but also kind of the how and the why of what I did. And it really helped me put my work in a new perspective. Think about what I've done and where I'm going, where I've been, and so on. So looking back, my career is definitely not something I would have predicted when I was 18 or 20. The path that I ended up taking, for sure had a lot to do with my abilities and my interests, had a lot to do with my limitations, my failures, what I discovered I couldn't do. But the path I took had as much to do, probably more to do with the people that I happened to meet and the places that I happened to land at particular times and the different ideas that I encountered through those different people and different places. So, excuse me. So for this talk, I've kind of constructed a story, a nonfiction story, more or less, pulling together and trying to connect those different landing points and people and places and ideas. It's a very incomplete story. It's a very abridged story. I could not mention all the people and places and events that influenced my work. And every time I went through my slides, I thought of someone or something else that I really should have mentioned. So apologies in advance to whatever and whoever I've left out of this story. So, okay, so I'm going to begin my story here in this place, and this is the city of Halifax. Halifax is in the remote but really beautiful northeastern corner of Canada in the province of Nova Scotia. And this is where I did my undergraduate college degree. I went to a small art college there called the Nova Scotia College of Art and Design. And I had always had an interest in the arts, but I really wasn't sure what I was going to do with that interest. Actually, one of my main strengths in high school was mathematics, but I had absolutely no interest in pursuing mathematics at the college level. Probably, unless you're in the art world, you haven't heard about the Nova Scotia College of Art and Design. The acronym here is NASCAD. Can you see my mouse, my cursor? Claudia, when I point?
Not in the moment. Try to point again.
You see the little?
No, I don't see you.
No, okay, all right. So I'm not gonna, okay, so I won't be able to point. Anyway, NASCAD is the abbreviation for the Nova Scotia College of Art and Design. And the book that you see here is from, it's fairly recent, it's from 2012. It's an MIT Press publication. And it's about the school during its heyday, during the 1970s, at the time I went to school there. And the title, The Last Art College, is a reference to this college being the last truly experimental art school, experimental in its vision, experimental in its pedagogy, similar in some ways to the Black Mountain College, another non-traditional art college from a few decades earlier. Anyway, in the 1970s, when I was there, despite the remote location of this school, or maybe even because of it, NASCAD, the Nova Scotia College of Art and Design, was actually one of the epicenters of the art world. In particular, it was an epicenter of conceptual art. And here on the left, you see Sol LeWitt, the American artist. He was one of the founders of conceptual art. And LeWitt was one of the many well-known artists who visited and taught at the school in the 1970s and helped shape its agenda. Other people like Klaus Oldenburg and Vito Acconci and Dan Graham, Robert Frank, other kind of early conceptual artists visited and taught at the school. And on the right here is Sol LeWitt's famous founding statement for conceptual art from 1967, which I'll read to you. In conceptual art, the idea or concept is the most important aspect of the work. When an artist uses a conceptual form in art, it means that all the planning and decisions are made beforehand and the execution is a perfunctory affair. The idea becomes the machine that makes the art. So the idea here is that you have a concept and it's manifested in some kind of plan, and then you just execute the plan. And at the school, at NASCAD, the Lithography Workshop was the main laboratory for making conceptual art. And lithography, as you probably know, is a kind of printmaking. And printmaking by its very nature separates the act of conceptualization by the artist from its execution, often done by someone other than the artist. The artist has the idea, the artist creates a plan for that idea, through a drawing on a lithostone, and then a master printer executes the plan by printing multiple copies of the original drawing. The guy you see here, I had to remember his name. His name's Bob Rogers, and he was my foundation studio teacher. And he was also the master printer in the lithography workshop. And I have no idea who this guy is. He was obviously the artist standing behind Bob Rogers, looking at the print. And here's one of Sol LeWitt's works from the lithography workshop at the school. LeWitt is widely known not just for conceptual art, but also for producing art through instructions, which are implemented by other people to create multiple outputs from that same instruction set. So this particular work was executed from instructions given in the title within a 20-inch square area using a black hard crayon. Draw 10,000 lines of any length at random. So here at the left are the instructions, the initial input for the printmaking process, and then at the right, you see the output of the process, the work itself. And the line here, the green wavy line, which I can't point to since you don't see my cursor, I guess. This green wavy line represents the execution of the plan, what LeWitt called the perfunctory affair. So at the school, I never actually got into conceptual art, but I was definitely influenced by what I saw there. I gravitated toward printmaking. I spent a lot of time in the lithography workshop. But then in my very last semester, I took a course in computer programming, which was offered for the very first time at the school. And when I took this class, I instantly fascinated with the possibilities of an algorithmic and a computational approach to design. It was a really interesting class because it actually combined computer programming with freehand drawing on large pieces of paper. So we went back and forth between programming drawings, I guess, and then on a large sheets of paper, practicing our freehand skills doing drawings. Computer programming was for me kind of a natural extension of printmaking. So instead of drawing lines on a lithostone, I could write lines of code, like you see here, to create not just multiple copies, but also variations by tweaking the lines of code, by tweaking the algorithm or the program. So the expressive power of code and programming really impressed me. And of course, as I pictured here, programming is aligned not only with printmaking, but also with the premises of conceptual art, and that important separation of the plan on the one hand and its execution on the other hand. And with programming, again, all of the planning and all the decisions, or most of them, are made beforehand, and they're encoded in the program, and the execution by the machine is what Lewitt called a perfunctory affair. So I graduated from the Nova Scotia College of Art and Design right after my brief encounter, my first date with programming. And I moved to Los Angeles. And that move was for strictly personal reasons, not for academic or career reasons. My partner at the time was a conceptual artist, still is a conceptual artist, and he was from Los Angeles, so we moved to LA. So I traveled from one corner of the continent, the northeast corner, down to the southwest corner of the continent, and I lived first in Venice Beach in an apartment on the boardwalk, which you see here. And I worked for a very short time in the model making shop of the architect Frank Gehry, working on models, physical models. This was in his pre-digital days. I worked on physical models for this project, the Hollywood Bowl project. And this was really my first encounter with architectural design. And I also worked as a window dresser for a clothing store in Beverly Hills. But I was always thinking about going back to graduate school to somehow pursue my interests in design or the arts combined in some way with computation or with computers. And at the time, I really had no idea. I had no idea of what that might look like, or if it was even possible. I also had the good fortune of moving after Venice Beach. I'd lived in a few other places. Then I moved into an apartment designed by the architect Rudolf Schindler. These are the Falk apartments. What can I say? It was beautiful. I can't point to where I lived, but we had a huge patio overlooking the Hollywood Hills. So living there was another, for me, another entree into the world of architecture. And then I discovered a program at UCLA in the Department of Architecture called Design Theory and Methods, which had a computation component, a computer component. And the head of the Design Theory and Methods program there was Bill Mitchell. And Bill was also the head of the architecture department and also a good friend of Frank Gehry's. And Bill, as you probably know, was one of the important pioneers of the field of computer-aided design and architecture. And in the 1970s, he was pushing his agenda in computer-aided design at UCLA. So I applied to the program. And I squeaked in because I had no real background in architecture, and I had not very much evidence of interest in architecture either. But anyway, I got in. Also, I wasn't interested in architecture specifically, but design more generally. Anyway, Bill became my academic advisor, and he introduced me to computer graphics programming and digital plotting and parametric design and more. So this is a photo of Bill from a few years before I entered UCLA, and he's standing with a digital plotter, which he was introducing to the architecture studios. at the time with very little support and very little enthusiasm from studio instructors. But most important for me in my career, Bill introduced me to a new computational theory of design at the time called a shape grammar. And shape grammars, as Claudia mentioned, have been the thread running through my work ever since that time. So for those of you who are not familiar with shape grammars, they're visual algorithms and they have rules or instructions, but the rules or instructions in shape grammars are not represented with text like Solowitz art instructions, and they're not represented with numbers or symbols like in a computer program. Instead, they're visual or spatial, expressed with drawings, as you see here, or they can be expressed in 3D with models. But despite this really big difference in the medium for the instructions of shape grammars, the original premises of shape grammars are actually very much, or were very much aligned with conceptual art and with Solowitz thinking. They were born, shape grammars were born in the early 1970s, right around the same time as the early conceptual art boom, and very shortly after Lewitt gave his definition of conceptual art. They were invented by two undergraduates at MIT, George Steiny and Jim Gips. And what you see here is the very first page of the very first publication on shape grammars from 1971. By Steiny and Gips, titled Shape Grammars and the Generative Specification of Painting and Sculpture. So they introduced shape grammars to the world here through the arts, through painting and sculpture. And Steiny and Gips distinguish right away between, on the one hand, the plan, or what they call the specification of an art object, and the actual physical art object itself. And just reading here from the text, they wrote, formally defining the specification of an art object independently of the object itself provides a framework in which theories of design and aesthetics can be developed. And then following that statement, they gave their proposal for an algorithmic specification or a shape grammar specification for art objects. And again, reading from the text, they wrote, the specifications introduced are algorithmic and made in terms of recursive schemata having shape grammars as their basic formal component. And then on the very last page, they reiterate their conceptual kind of approach, and they write, for design theory in the visual arts, this generative specification means that the definition and solution of design problems can be based on the specification of an art object instead of the object itself. And the specification here is the plan that's defined entirely in advance of making the actual thing. And here they are in 1970 or around 1970, exemplifying their position. On the left is a generative specification, the shape grammar, the instructions for a painting, and on the right is an actual painting that they made based on the shape grammar, the result of executing the rules. George, if you don't know these two guys, George is standing on the left and Jim on the right. Right, so the most important difference here between a shape grammar and a computer program or art instructions is that the shape grammar rules are visual. And George and many others have written on and elaborated on this really important point over the years. So here close up is what a shape rule, very simple shape rule looks like. And basically a shape rule it's kind of a conditional or an if-then statement. It's like an if-then statement in a computer program. If you see the shape, the drawing on the left side, then you do that too. That's what you see on the right side. So when Bill introduced me to this visual paradigm at UCLA, I thought, well, wow, here's a design approach that really resonated with my interest in design and the arts and also in computation. So now instead of writing lines of code, a program that needed to be translated into visual artifacts, I could work directly with shapes as code. And the medium of the input is exactly the same as the medium of the output. There's no translation necessary. And also with shape grammars, unlike most computer programs and unlike much of early conceptual art, that space, that wavy green line in between the input and the output is really no longer a perfunctory affair. It's a very rich and detailed and expressive affair. So here is what's actually happening in that space, the execution or computation with the rules. And here is, the source of much of the expressive and explanatory and communicative power of shape grammars. And opening up this space has been a foundational aspect of shape grammars from the very start. It was never meant to be perfunctory or invisible. It was meant to be seen. The computation, the execution space was meant to be seen and to be meaningful. So getting back to my story, when I was a graduate student at UCLA, George Steiny arrived there as a visitor, and Bill had invited him to come. The two of them had just completed the first shape grammar for architecture, a shape grammar for Palladian villas, and that was a major milestone in shape grammar work. And Bill and George were doing some follow-up work on that grammar in connection with an exhibit of Palladio's work at UCLA. They were working also with the historian Howard Burns, who I re-met when I moved to MIT. I re-met him at MIT through Bill and co-taught a class with him with another colleague, and the class was also on Palladian villas. We actually went to visit Palladian villas. So little did I know back in whatever it was, I guess the early 1980s, that Howard Burns would come back into my life at MIT, and I would end up teaching a class with him. So here's a simplified step-by-step computation of a Palladian villa using the rules. This is that, what I call that execution space between the rules and the output, explaining how villas are composed. So while I was at UCLA, I came to know George very well. I also came to know Jim Gips very well, who was teaching in the computer science department at Boston College. And my first foray into shape grammars as a grad student was an analysis of Hepplewhite chairs. I wrote this very simple parametric grammar to generate designs like the ones you see here. I published my first paper in the journal Environment and Planning B, and that was really the first step in my academic career, though I didn't know at the time that that's where I would go, that I would go into academia. Anyway, at the time, most shape grammar work was analytic, including this Hepplewhite grammar. So shape grammars had mostly been used to describe, analyze designs from the past or contemporary designs. But I was coming from a creative arts background. I was really more interested in how shape grammars could be used, creatively to create new things, to invent new designs, and shape grammars could be used to understand how new designs could be invented on the basis of existing ones, how designs evolve over time. And that interest led to my master's thesis and then to my PhD dissertation. So I started looking at the work of designers and architects and artists and how their work evolves over time, how they innovate, how they invent new styles on the basis of previous ones. And this is one body of work I looked at, the work of the 20th century artist George van Tongerloo. I looked at his paintings over almost his entire art career, a period of about 20 years. He began painting in a kind of de Stijl, very strict de Stijl, horizontal, vertical paradigm, and then he ended up 20 years later with paintings with really no obvious connection to de Stijl. And he identified different stages of the development of his painting, which you see here. And then from that example and several others, I developed a formal model for showing how designs evolve over time. And my basic idea was really simple. So instead of describing transformations or changes in the designs themselves, which is the typical art historical approach, I describe the transformations at a deeper level and in the rules underlying the design. So the idea was to look at the underlying logic of designs and show how that logic or those rules transformed. And then I applied that model to several case studies, including the van Tongerloo example, which you see here. I don't have time to go into any detail of this, so I'll just move on, talk about people. So here I have to mention another really important person in my life, Lionel March. Lionel was one of my doctoral mentors. He was a reader on my doctoral committee. Lionel really didn't have a direct influence on the work that I did for my PhD, but he was a huge, huge supporter and promoter of my work. And he always had incredible insights and great feedback and wonderful references for me to follow through. And he was just generally a fun person to be around. I mean, I learned a lot from him. Lionel became chair of the architecture department at UCLA right after Bill left UCLA for Harvard, which I'll get to in a minute. So after I graduated, I published I revised my doctoral dissertation, published it as a book. That was another important part, actually a necessary step of my progression, through an academic career. But while I was doing my PhD, I still wasn't sure whether I'd go into academia or whether I might pursue a job in industry. So around the time, when I was working on my dissertation, there were software companies looking for graduates of design programs with computation expertise like me. I ended up deciding not to go in that direction because I really did not like the headhunters who came to UCLA, and I really was not interested in the projects that they were interested in. So I started on an academic path. I was hired at UCLA for a year as a postdoc and also as a lecturer. I taught a class on parametric design. Then I left and was basically unemployed for a bit. And then I was hired at UCLA as an assistant professor, thanks in large part to Lionel March, who was head of the department at the time. It would not have happened if Lionel hadn't been there. And then 5 years later, I got tenure at UCLA. Now, why am I showing this picture? This is a photo of Robin Liggett, and she doesn't know this probably, but she's the person most responsible for my academic career. Robin was an assistant professor at UCLA when I was a graduate student there. She taught computer programming and computer graphics for architects and urban planners, urban designers. And when I was a student, I watched her go through the tenure process, and I was asked to, as a student, I was asked to write a letter for her tenure case. So I saw what was happening. She was the only woman faculty member in the department when I was a student. And when I joined the faculty, I was the second woman faculty member. And when I went up for tenure at UCLA, I don't think I would even have tried doing that. I couldn't really imagine doing that without having Robin there as a role model. I would have just leaked out of the pipeline. And I wasn't mentored by Robin. It was just her presence that made it possible for me to go through the tenure process. Just seeing her as a tenured professor made it possible for me to do it too. So it's really, really critical to have role models when you're in the minority in a group. So thank you, Robin. Robin is retired now. Of course, in order to get tenure, I had to do research beyond the PhD and published, and much of my early work was focused on expanding the expressive power of grammars and their potential in creative design. I'll just show some excerpts of my work from that time. So shape grammars at the time were about form and composition. I looked at how qualities of form might be incorporated into shape grammars, including color and texture and light and materials. And with that in mind, I developed something called color grammars. I also embarked on research and a series of papers proposing how shape grammars could be used in creative design, including a pedagogy for using shape grammars and color grammars in design education. And this work took off in part from an early paper by George Steiny on kindergarten grammars. And then I used that approach, that designing with grammars approach, in my teaching at UCLA and then later at MIT. These are just examples of student work using shape grammars in many different areas of design: architecture, structural design, jewelry, typography, sports, art, crafts, car design, fashion, lighting, even music. One of my students wrote some grammars for musical instruments. Then after about 8 years at UCLA, I made another cross-country move. Bill Mitchell, my PhD advisor, had moved to the Harvard GSD Graduate School of Design after I got my PhD. Then he moved to MIT to become Dean of the School of Architecture and Planning. And you can make out up at the top, I'm sorry, I can't point, you see the word architecture. The Department of Architecture is on the front face of MIT on Massachusetts Avenue, one of the first departments at MIT. Anyway, like he did at UCLA and then at Harvard, Bill started building a computation program at MIT, and he asked me and he asked George Steiny to come to MIT and help that effort. I resisted. I resisted for a year or two because I had a happy home at UCLA. But then in 1997, I finally relented and I moved from Southern California to Boston. And I was met with this. So this was a huge shock, having lived in LA for almost 25 years. My first winter there, we had record-breaking snowfall. But happily at MIT, I met another important person in my life, my academic life, my personal life, and that's Larry Sass. Larry was a PhD student when I first arrived at MIT. His research involved digital fabrication. He was actually working on a Palladian villa construction grammar with Bill Mitchell for his PhD. He was later hired as an assistant professor. He developed the first, single-handedly, the first fabrication lab for the department. And he was really a big part of the push in the early 2000s to introduce digital fabrication into the architecture studio. And so in this kind of a new environment of growing interest in fabrication, construction, and thinking about the relationship between designing and making, my own interests began to shift. And my interest shifted from design, from abstract design, using shape grammars to generate representations of things to be made, to thinking about grammars, using grammars for actually generating the things themselves. So in other words, shape grammars had mostly been used to generate designs, like what you see here on the left, designs for things. So they were used to generate representations for things with shapes, but not to generate the things themselves. And of course, the properties of the things themselves and the way those things are actually made can be very different from the way the designs for them are made. So I just started rethinking the whole shape grammar enterprise, its focus on abstract mathematical shapes and as representations for physical things. And I started thinking about grammars with rules that operate on and generate the things themselves. And that brings me back to Sol LeWitt and his perfunctory affair, that hidden execution space, the hidden computations of his work. So what's actually happening in this particular instance, in this space between input and output, is this, the draftsperson actually drawing lines on the stone. Like, this is a real-time, continuous, embodied temporal material process. And that process on the face of it seems very different from an abstract computational process, certainly different from a shape grammar computation. So having worked with shape grammars for many years, I wondered, like, what exactly is the relationship between abstract formal computation and active embodied physical making? And one obvious difference between the two is that a computational process is discrete, it's discretized, it happens in discrete steps. And a real world process is continuous, but both are the same in that they both occur over time. They're both temporal processes. And that temporal process happens here in that space between input and output. What happens at the top is continuous and what happens at the bottom is discrete. So I started to wonder, like, is it possible, does it make sense to represent a continuous process like physical making, which is computational, and discrete. How to represent a continuous process as something computational and discrete in separate steps. And it turned out, after I did some work on this, that there's a lot of research on the temporality of continuous real-time processes and events and actions in the world, including making. And a lot of that work is coming out of the field of cognitive science. And a key idea here is that in order to kind of understand and make sense of this kind of continuous multisensory stream of actions in the world, what people do is we actually chop up and segment that continuous flow of actions into discrete temporal parts. So just like we recognize physical objects and things by segmenting them into spatial parts, we understand events and actions by segmenting them into what are called temporal parts. And this idea is actually central to work, important to work in AI and robotics in order to build computational models or robots for recognizing human actions and generating human-like actions. And not surprisingly, researchers often turn to grammars as a way to represent and parse up actions and processes and times into discrete temporal parts. And this is where shape grammars have potential and where I come back in. So shape grammars, shape rules very naturally suggest temporal segmentations of a continuous process. The arrow, which you see up at the top in the rule, can represent an action in time. And the rule applications or computation, like the one you see at the bottom, defines a temporal segment, step-by-step segmentation of a potentially continuous process. So the focus of my work over the last several years has been on how grammars might be used this way to understand, to model, and to even teach and to learn real-world creative processes. And in order to do that, I need to show how rules can encode kind of not just the temporal aspects of making things, but also the sensory and material aspects of making things. So to do this, I adapted the shape grammar formalism for computing designs to define what I call making grammars for computing things. And that was done by extending the function of a shape rule from see this, do that, to a more general sense this, do that. So the left side of a making rule extends to all of the senses, and the right side, the do that part, includes any type, could include potentially any type of physical action, drawing, looping, folding, painting, and so on. And at the same time, I formed a research group, finally, with my students, which we call Computational Making. We launched this website, which is very much out of date. Now I haven't really done anything since COVID started on this website. Anyway, to conclude, I'll just wrap up in a couple of minutes. I'll show you a few excerpts of my work, from my own work with computational making and making grammars. So this was a project inspired by quipu. These are knotted strings made by the ancient Incas as a recording device, physical record keeping and communication device. Making these quipu is highly tactile. You can do it with your eyes closed. It's a good case study for exploring the potential of rules for making things. They're made of knots called overhand knots. And what you see here on the left are some schematic rules for quipu knotting. There are rules for looping, and there are also rules for changing the position of your hands on a string. Important thing here are actually the red marks. The red marks indicate the positions of the maker's fingers on the string. And this is really the most challenging, challenging part of trying to formalize physical and sensory actions, how to indicate the role of the body and the senses and rules. So the red marks here and in other making grammar projects indicate the maker's kind of sensory, physical actions, interactions with the things made. And with respect to temporality, the rules capture here kind of natural kind of stopping points in a continuous process. So each rule defines a temporal segmentation of that process. And on the right is a computation of a quipu, and it discretizes, it separates out a continuous knotting process into separate steps, but in a way that intuitively captures natural stopping points in the process. Another case study had to do with column pattern making. And these are self-intersecting curvilinear patterns made by women in front of their homes using rice powder. It's a highly skilled, creative, temporal, improvisational process. And it's a good case study for showing the difference between shape grammars for creating representations and making grammars for creating the things themselves. So it's very straightforward to write a shape grammar to generate the designs with just a few rules like the ones that you see here. They just take motifs and they pop them into a grid. But these rules don't capture in any way the actual temporal improvisational performance of making column. The way women make column is very different from what the rules encode here. And to capture the live kind of temporal performance of column making requires many more rules that might look something like the ones that you see here. The basic principle here is weaving, which is very different from placing motifs in a grid. So the rules here are meant to encode the different kind of discrete gestures of the column maker. The red dots, which you may be able to make out in the slide, represent the maker's focus of attention, where she's looking in making the patterns in order to decide the next move to make. And this is what a computation might look like. The computation is very long, takes time, but they begin to show how an abstract, discrete computation, that time in between the input and the output, can express a continuous and temporal and performative dimension of a creative making process. And then last, in a current project that I'm working on now, I'm returning to work that I did as a PhD student. After so many years now, I'm not afraid to look at what I did in my PhD. It's part of my self-reflection and reevaluation of the whole shape grammar enterprise. So when I did that work on von Tongerloo, which I showed before, I did a similar study looking at the work of Fritz Glarner, a Swiss artist, who also began his work in a distill style, but it evolved very differently than von Tongerloo's. And Glarner is known for his work on relational paintings. So I developed for my PhD, I developed shape grammars for his paintings, but those shape grammars really were not meant to capture how Glarner actually made the paintings. So now I'm looking at his sketches for his paintings and figuring out like how to encode and describe his sketching process in rules, with rules that incorporate decision times, deciding what to do next, and also action or drawing times. And no surprise, the rules are turning out to be more complex and numerous than the rules of the original shape grammars, and very, very different in terms of what they show. So that's where I am now. I'm looking forward to getting beyond COVID and quarantine so I can think straight again. But I am thinking more and more now about kind of the larger sociocultural context and environment and world in which designing and making happen beyond the things made and the maker, and how that all relates to computation. And probably that thinking has a lot to do with events in the United States in particular over the last year. Anyway, we'll see where that goes. So I'll stop here. That's the end of my story for today. Thank you very much. I'll turn it over to Claudia.
Thank you very much, Terry. That was absolutely fascinating. It's a very, very interesting journey that you described there. And I think while I knew the bits of your work, it's very nice to sort of see it all come together. And I think maybe just 2 comments before we open up the discussion on a personal level. I think one thing is that you also were, for me, one of those role models, like Robin for you, because you were one of the very few academics that I had encountered who was a committed mother and an academic. And I think, again, for that, I thought it was great to have a role model, and you were that role model for me. So
thank you. I'm glad I served some function.
No, absolutely.
A really important one, yeah.
It is a very important function. It's a good thing that you've highlighted this, and that's one of the reasons why we invited you as a woman for a talk, because we feel that it's really important also for younger academics to have women as role models. And I think the other thing is it looks as if we're getting closer to actually having a knitwear grammar, where you do have the structure plus the making coming together in order to really describe the forms, which is what I was originally interested in when I encountered your work. But I suggest, since we have got a small group, that that you all open up your cameras and your mics and we'll have an open discussion. So have we got any questions for Terry? Do you want to stop sharing, Terry? Because then you'll
Yes,
see
because I can't see anyone unless, yeah.
Yeah.
I'd like to add, Claudia, and it's, oh, there's John. Hello, John.
Hi, Terry.
Hi, nice to see you in your space.
And you.
I want to say that, Claudia, you were also a role model for me with your knitting.
Yes, I'm still trying to lift the.
And there's Warren. Warren.
Hi, Terry.
Hi. Fancy meeting you here in
Yes.
a place like this.
Have we got any questions for Terry?
Actually, I have a question. You were doing this, what would be thought of as very intellectual work in two design schools, UCLA and MIT, and I was just wondering what was the reaction of your colleagues to what you were doing?
That's a complicated question. Depends on who you consider my colleagues.
Well, I'm thinking actually more of the professors of design.
The architects, the
Yes.
architecture.
Mm.
Oh yeah, it was very bad.
Mm-hmm.
Warren, keep this to yourself. When we first came to MIT, the studio folks were outright banning computers in the studio. They didn't even want students to show their work, anything that had been done on a computer. So it was very, it wasn't me and it wasn't George. It was just kind of anti-computers. But a lot of that had to do with Bill Mitchell, and Bill Mitchell taking over as head of the school, from outside. So there was resistance to Bill. But now it's very acceptable. Now everyone, is fine with it. And they've come around. As far as, grammars, some of my colleagues would tell me, well, Terry, it's fine, you're doing this work with grammars. Yeah, you can do that. That's fine, but that has nothing to do with architecture. But the person who said literally that to me in probably the year around 2000 ended up writing a book where she mentioned like using rules, how important it is to use rules in parametric design. So, it takes time.
Yes.
It takes time. There's a similar story at UCLA. Yeah.
Can I actually ask you a research-related question? You were saying at the very end that you're beginning to be more interested in the context affecting things you're making grammars and the shape grammars. And I was always interested in the context of shape grammars, in that relationship between the context and the artifact coming out of the rules of making. And I was wondering what your thoughts are on that, because on some level shape grammars are a very reductionist way of describing things. On the other hand, it's a very powerful way. And to me, this always posed extremely interesting questions around the role of context. So I was wondering what your thoughts were on that.
Yes. Okay. So yeah, that kind of brings me to some of my final words. So making grammars are an attempt to get beyond the abstract shape representations and they're mathematical representations of things, which George has worked on. So with making grammars, I wanted to bring into view the actual physical things and their materiality and the temporal aspects of making them, and bring in the maker. All those red marks are an attempt to show the context of the maker being there and doing things to things. And it's very difficult to show graphically, of course. But I'm also thinking about the larger environment and how to show the larger environment, because it's not just the maker and the thing in isolation. There's the bigger context, right?
Yeah.
And how to show that. I had some students attempting to do the same thing. I had a student who who developed what he called effort grammars that showed the amount of effort put into making something. Some of that had to do with the calculation of effort, had to do with the surrounding context, but it wasn't shown explicitly.
But
I
that's
don't know if that answers your question.
A relatively narrow description of context, because I think listening to your career trajectory, and I think previously to John's, it's interesting how you've been influenced by the ideas that were current, like the conceptual design, and then the computer technology came up, and then the rapid manufacturing became much more advanced, so it became possible. So there's really big context and trajectory of thoughts had an immediate effect on you as a designer. And similarly, I think other designers are affected by the big developments, and I'm wondering how they sort of could get incorporated or accounted for.
I don't know, but I do know that I am thinking more about environment, again, especially because of events in the world and what happens when you put these models out into the world and who uses them, who makes them. It's really important and can't be ignored anymore. Warren.
Yeah, Terry. As you were speaking, I was looking at your drawing of the squares.
Yeah.
And noting that the position of a square with respect to the previous square varied a bit along the way. And so that brought ambiguity into my mind. And I'm wondering, what is the role of ambiguity when you're thinking about shape grammars?
That's a topic that you probably know George has written a lot on, or maybe you don't know.
No, I didn't, but now I'm going to go find it.
That's very cool. Okay, well, I will have to tell George. Yeah, George has written a lot. I actually wrote a paper too on ambiguity. And ambiguity enters in when, whenever the person or the machine or whoever it is that's using the rules or developing the rules decides what to do next and what to look at or what to feel. Yeah. So it's ambiguous what might happen next. So
it's sort of creative, but in a context.
Exactly. Yeah. So if the rules are predefined, then the creativity might be circumscribed by the rule in certain ways, but not necessarily predictable what might happen with certain rules. Yeah.
Terry, why is that a form of ambiguity rather than a form of either random or deliberate selection?
Say that again.
Why is this a form of ambiguity rather than either deliberate or random selection?
Because it's the ambiguity is in, well, now I'll just go back to shape grammars, and this is really George's domain and his main interest, in that when you're looking at a drawing, it's the parts of the drawing are not predefined, so you can see it in any way. The drawing is ambiguous in that sense. That can be read in different ways. That kind of ambiguity. Does that answer your question? So you can see a drawing as a duck, or you can see it as a rabbit, and you can pick out the rabbit, or you can pick out the duck, and you can write a rule for a rabbit, or you can write a rule for a duck. So it's ambiguous in that sense.
But only to the human viewer or to the
Yes.
Yeah.
Yes. Yep. Yeah. And harder to make a machine do that. But again, that's George's life.
Along those lines.
I have a different kind of question.
Yes.
One of the issues I always find with any formal system is that there's some mismatch between that and what humans do. And what humans do has a dynamic associated with it, which changes their perception of what's happening.
Yep.
And I'm wondering, if you had such a thing called a dynamic, word dynamic in front of what you're doing, what would that do? I mean, could you imagine a shape grammer that changes itself as it's being used?
Well, that's what people do with shape grammars. If they're designing with shape grammars, they're constantly changing it. It's not preset. And yeah, I can imagine a machine doing that. There have been some attempts to do that. I'm thinking actually not of a grammar, but of David Cope, the composer, his work, where he essentially used grammars for musical composition. And the program he wrote, yeah, would learn. It was a self-learning program that evolved over time and churned out different grammars and different compositions. So yeah, it's possible to do that. And you're right, people do that all the time. Unless you're writing an analysis grammar, then it's kind of set in stone, right? You just decide what it's going to be, and you really don't want ambiguity and emergence that much. You want it to do something predefined. But in my classes, my students are always adapting their grammars and changing them, seeing what happens, and then changing the rules. And yeah, it's like any design process. Definitely dynamic is the right word.
So when you move, oh, please go ahead, Martin.
Oh, yeah, you finished that thought. I'll ask a question in a minute.
I'm just following up on this. The temporal structure is a rather special one, I think, with ambiguity, because there, when you move to sense and respond, you put in place a whole temporal structure of things that can happen. And so that's not exactly ambiguous. It's rather sort of tracking the environment in some way.
Yes. So from what I understand from cognitive science, it's very, very interesting what people do or can do and can't do with respect to continuous events. So in order to recognize something like making a bed or slicing an apple, we're looking for certain chunks happening in a certain way. And if they don't happen in that way, we don't recognize that action as making a bed. But in a creative process, it's possible probably to chunk things in different ways to get different outcomes and have some ambiguity that way. I'm not exactly sure how that works with drawing, and but it's really interesting to think about, to come up with new ideas, new possibilities by chunking in different ways and seeing things in different ways just by fooling around with that temporal segmentation. So we don't want that to happen in the real world, otherwise we'll get really screwed up and not know what anyone is doing, right? But in a creative process, it can be a very different story by thinking about the temporal segmentation of a creative process, like drawing and seeing it in a different way and chunking it in a different way. I had some students do some studies like that with drawing, but they were very short and not in depth enough. But yeah.
But it sounds almost as if this is the place where shape grammars meet situated cognition, because that was one of the things I was always wondering, that we think so much by recognizing what to do next, even if we couldn't formulate the plan. And in a way, it almost seemed like the opposite of a grammar where all the steps are predefined. But maybe with the temporal thing, it would be a neat way of bringing it together.
Yes.
Isn't the point about the grammar approach is that it's inherently situated?
That it's what?
Inherently situated.
Well, it's situated with respect to the viewer, the human, using the grammar. You said inherently.
Well, it's situated with respect to the operation of the grammar, surely.
It's situated with respect to the perceptual apparatus of the person either making and or using the grammar and the rules, depending on what the person is seeing or feeling or whatever. So it's situated in that respect. So the way shape grammars have evolved, and certainly the way George describes shape grammars now, is really more like a making grammar, because he describes shape grammars in terms of actual drawing, seeing and drawing. So it's a perceptual affair involving a person or a really smart, whatever, computer or robot.
Which looks to me, as a once psychologist, as the production system view of how thinking is.
I'm not going to go there because I don't know how people think. I'm not even going to go there. Sorry. I can only observe what people are doing. Who knows what's going on in their heads, right? Yes, but yeah, the situated aspect is interesting to me. And the physicality of things and the physicality of processes are much more interest to me than they were, 20 years ago or 30 years ago.
Because with some of the things that you used as examples, it's probably something very situated that you kind of know what to do once you've got there, and that this is something that's sort of ancient memory that we keep for a very long time.
Yeah, yeah. So what bothers me now about shape grammars is that, and the work, when I look at the work that I did originally with shape grammars, it's true of computer programming too, is that there are a lot of tricks involved to make a shape grammar look elegant and short and produce the right output. And they'll work to produce the right output. And I wrote some grammars like that, and I was very proud of them. Like, oh, this will do the trick, and 3 rules, and I've got this tricky, labeling system to make it work, a control device, as nothing to do with, what's actually happening when, something is made. And when you look at actual processes like the, videos of women making kolam patterns in India, it's amazing. They do it on site every day in front of their houses. It's they do it a lot. So obviously they have a lot of experience, but they just make these patterns huge patterns on the ground, and they come back to the beginning. They manage to, figure out how to make these self-intersecting curves that come back to where they started. And the shape grammar that I showed you has nothing to do with that process at all. In no way captures that process. And the shape grammar is, it's elegant, it's cute, it's like, wow, I can do this in 4 rules and I get the right results, but so what?
Actually, that raises
so for me, so what? It's much more interesting what these people are doing.
That raises quite a fundamental question, which is whether the doer has a perception of how they're going to get to the end, or whether that's simply a consequence of what they do.
Yes, I think it's a little bit of both. Mm-hmm. Because they have so much experience and women have been doing this since childhood, they do have some perception of how to get to the end, somewhere in their bodies and their brains, but they're not exactly sure, because the creativity of those patterns is very important. And apparently these women get together and they discuss the patterns that they made that day and, how it's different from what happened. So the important goal is to create patterns that have not been created before and to do that on the fly. But at the same time, they have this embodied experience and know-how. Yeah, and they do make mistakes. And I didn't incorporate that in my grammar because that's also really hard to incorporate mistakes. But when they incorporate mistakes, they do things to adjust, like they'll make the pattern bigger than they anticipated so that they can incorporate the mistake and change the pattern, on the fly. Yeah, incorporating mistakes is important too. And how you do that with a rule-based system is interesting to me. It's very interesting to me now.
So,
yeah.
Terry, this is all fairly new to me, and so maybe this is a conversation we should have when there aren't experts around. But to me, you're suggesting that one role is replication, that shape grammars can replicate something.
Yeah.
And then there's a synthetic role, which is a very different thing.
Yes. Yes. So there's the initial work with shape grammars was mostly replication or analysis, using rules to replicate what has already been done and show something about the composition and form of those things, to elucidate the underlying kind of compositional aspects.
Right.
And then there's the synthetic or creative aspect of using rules to make up rules to make things that, or to design things that haven't been designed before, which is what I do in my classes. So I ran through those slides really quickly of student work with grammars in different areas of design. It was all creative design, making up a new typeface, making up a new structural system, coming up with new architectural designs, creating new musical instruments. Yeah.
Oh, what fun.
Yes, it is a lot of fun.
I should take your class.
Some of your students have taken my classes and done really well.
Oh, good.
Yeah. I didn't give enough credit to my students because I always in my class, I give very open-ended assignments so that I make students come up with all the good ideas in their projects. And they do. They come up with great ideas, things I never would have thought of. Yeah. Including the mechanical engineers, product designers from your department. Yeah. Well,
Terry, thank you very much. I think we should probably conclude the seminar since they are notionally an hour. But thank you so much. It was really, really interesting. And
thank you, Claudia, and thank you all. It's really great to
that was really
great
nice
to have this discussion. I really feel like Zoom. Well, this is not Zoom. Whatever it is worthwhile bringing people together from near and far.
Yes.
It's really nice to see you.
Yeah.
All, and hope to see you in person
soon.
Very soon.
Great. Yeah.
I hope you're all well and stay well for the next few months.